Shifting our focus now to something scary that's unfolding miles away. It serves as a wake-up call for all of us.
Antarctica was supposed to be the quietest place on Earth. But when scientists dropped microphones beneath its frozen seas, the silence shattered.
This sound got its name because of the fact that the sound descends in frequency over about 7 minutes.
From miles under the ice came a sound, steady, mechanical, and not alive. At first, they blamed the equipment, then the weather. But when artificial intelligence analyzed the data, it started connecting patterns too deliberate to ignore.
Scientists were able to locate the sound as coming from somewhere off the Antarctic peninsula.
Whatever it was moving.
This knocking sound was picked up by an underwater hydrophone, and for a while it had people stumped until they were able to find the culprit.
And what it revealed turned the world's most lifeless continent into one that suddenly felt awake. The strange sound beneath Antarctica's ice. The ocean that circles Antarctica might look frozen and still, but beneath that icy lid, it's alive with sound. Drop a microphone below the ice, and you'll discover an entire world of voices.
Can enable us to sample and get to very rare Antarctic blue whales.
Deep moaning calls of blue whales drift through the dark. Leopard seals sing eerie songs that echo like sirens. Wind howls through cracks in the ice, and threading quietly through all that natural music is a sound that doesn't belong, a slow, steady hum that moves. It drifts across the recordings like a train passing in the distance. That low hum isn't nature's work, it's mechanical. Scientists studying the Ross Sea recorded it using underwater microphones called hydrophones, set in place to listen month after month. Those instruments caught the voices of whales.
The sound was indeed captured under the water, and these are the sounds of fish calls.
The groans of ice, the thunder of storms, and within those same frequency bands, they caught something else, the unmistakable tone of machines. The recorders were placed in unforgiving locations. One was near the remote Balleny Islands. Another was deep inside a region called Terra Nova Bay, a place known for brutal winds that sweep down the coast so fiercely they blow the ice away, leaving a patch of open water called a polynya. Even during the heart of winter, that gap in the ice remains open, a kind of window into the sea. And through that window, the hydrophones listened without pause. They kept recording through storms, calm days, freezing seasons, and long darkness, capturing how the soundscape shifts with the weather and the ice. When scientists later examined the recordings, they realized the ocean was anything but silent. There were natural sounds, and layered through all of that were faint but steady lines from human activity. Ship noise. It slipped under the ice, traveled through open leads, and showed up where no one expected it. That might sound strange, but the reason is simple. Sound travels incredibly well underwater, especially low-pitched sound. In the open sea, deep cold water bends those low tones into a kind of natural tunnel, a sound channel that lets them travel for hundreds, even thousands of miles without fading much. It's the opposite of light. Light dies quickly underwater, but sound goes everywhere. That's why a blue whale can be heard far beyond the horizon.
While the low part of the sound would make sense to attribute to the baleen whale,
And why a ship's slow drone can roll through the deep like distant thunder. The pressure, the cold, and the layering of the ocean trap that sound and carry it along like a hallway of echoing waves. When researchers turn those recordings into spectrograms, pictures of sound where time runs left to right and pitch runs bottom to top, it's like reading the ocean's diary. Deep blue whale calls paint dark, heavy lines near 20 hertz. Leopard seals leave bright, sweeping curves that look almost like drawings of light beams. The creaks of ice and the hiss of storms fill the background with shifting clouds of texture. And then, in the middle of it all, appear thin, ruler-straight lines. Those lines sometimes bend slightly, showing motion. They're not whales, not weather, not ice. They're ships, faint, but undeniable. The Ross Sea recordings revealed the complete orchestra of Antarctic sound: animals, wind, weather, ice, and us. The challenge now is sorting through it all. These hydrophones collect so much audio that no human could possibly listen to it all. So scientists brought in artificial intelligence to help. The Australian Antarctic Division, working with international partners, has spent years building a massive library of underwater sound using floating microphones called sonobuoys and fixed recorders anchored to the seafloor. In the last few years, they've trained AI systems to comb through this mountain of sound and recognize who or what made each noise. They use algorithms to pick out blue whale songs, fin whale harmonics, and leopard seal calls across the Southern Ocean. But those same algorithms also tag the things that don't belong: the flat, mechanical tones of engines and sonars. I can tell them apart because a ship's sound looks completely different from an animal's on a spectrogram. These systems learn the same way AI models learn to recognize cars or faces in photos. When a ship slips beneath the frozen edge or passes through an open lid, it leaves a trace of low, steady notes on the recording. Each note comes from the rhythm of its engine or propeller. As it moves closer or farther away, the pitch bends slightly, just like the change you hear when a siren passes on a highway, a phenomenon called the Doppler effect. Scientists can use those bends to estimate motion. The way the lines tilt tells whether the ship was approaching or leaving. Their spacing hints at speed. If several microphones are placed apart in the same region, researchers can compare the tiny differences in when the same sound reaches each one. Even a delay of just a fraction of a second is enough to calculate direction and velocity. It's a form of underwater triangulation, and it works astonishingly well. Some computer models can even track more than one moving source at once. If the microphones are synchronized, the ocean practically tells you who's out there and where they're going. And that's crucial in Antarctica, where most of the time, there's nothing to see. The weather hides everything. The darkness in winter is total. Yet beneath that darkness, these microphones are still listening, still tracking movement. It's the closest thing to having eyes underwater. So why track this at all? Because the human footprint in Antarctica is growing every year. Research vessels, krill fishing fleets, tourist liners, and supply ships all pass through these waters. And the low-frequency rumble of their engines is the loudest man-made sound source in the ocean. Even ships hundreds of miles away leave acoustic trails that can mask or disturb the calls of marine animals. For whales that navigate and communicate by sound, that interference is like static over a phone call. It can drown out crucial signals and change their behavior entirely. This isn't speculation. Scientists have been warning about it for years. And in the Antarctic, where ecosystems evolved with almost no human noise, the concern hits harder. The Ross Sea, where many of these recordings were made, is one of the planet's largest marine protected areas. About 600,000 square miles of ocean meant to preserve a rare, nearly untouched ecosystem. The Antarctic Treaty System and the International Polar Code both set rules to reduce environmental harm. Crews are urged to avoid known whale habitats, heavy fuel oil is banned south of 60 degrees south, and ships are told to take routes that limit their impact. But there's no volume knob for the sea. Those regulations only matter if we can measure where and when the noise happens. That's exactly what these hydrophones and AI tools are doing, building the first real acoustic map of human presence in the Southern Ocean. There's another layer to this story. Antarctica is full of strange, powerful natural sounds that can easily be mistaken for something else. Years ago, a mysterious signal known as the bloop set off wild theories about monsters in the deep. It turned out to be nothing living at all, just the sound of ice breaking, a kind of undersea earthquake caused by massive slabs of frozen water snapping apart. That discovery taught researchers a key lesson. Unless you can tell the difference between life, ice, and machines, you'll keep misunderstanding what the ocean is saying. With better sensors and AI sorting the data, those boundaries are finally clear. The network of underwater recorders is growing fast. NOAA's Pacific Marine Environmental Lab has described long-term installations designed to gather years of continuous data in Terra Nova Bay and the Amundsen Sea. Each one contributes to a vast sound library that helps train AI systems to recognize patterns across seasons. Because low-frequency sounds travel so far, just a few well-placed microphones can cover enormous areas. A lifesaver in a region where deploying equipment is dangerous and expensive. If AI can isolate a single unnatural hum slipping under the ice, it begs the question, what else is moving beneath Antarctica's frozen shield that we've never seen before? The answer will take us from sound to something even stranger. AI maps Antarctica's moving underworld. Beneath Antarctica's thick ice, the world is not frozen in place. Water flows through the dark like blood through hidden veins, creeping between rock and ice, pooling, draining, and sometimes surging with enough force to lift miles of ice by a fraction of an inch. For decades, we only saw hints of this motion, small rises and dips in satellite data that made no sense. Now, with sharper satellites and artificial intelligence sorting the noise, those faint signals have turned into a map. What it shows is extraordinary. A vast underground network of lakes and channels that fill and drain beneath ice up to 1 mile thick, reshaping how the entire sheet slides toward the ocean. This is no longer guesswork. It comes from over a decade of precise height measurements and new AI tools that can pick out the fingerprints of moving water with stunning accuracy. At its simplest, a subglacial lake is just a pocket of liquid water trapped between bedrock and the ice above. The pressure of that much ice, tons upon tons pressing down, lowers the melting point, keeping the water from freezing solid. A bit of geothermal heat from the rocks below helps keep it liquid. Some of these lakes sit still for years, while others act more like valves, filling up slowly and then draining through channels downstream. You'll never see a river on the surface, but the ice above still tells the story. When a lake fills, the ice rises ever so slightly. When it drains, the ice sinks. Satellites equipped with radar altimeters can detect those changes, sometimes just a fraction of an inch, sometimes a few inches. And by tracking them over many years, the picture sharpens into a breathing, shifting system. The big breakthrough came from Cryosat-2.
The Cryosat-2 satellite built by EADS Astrium will survey these natural and man-driven changes.
A European Space Agency mission designed to measure the height of ice sheets with radar. Unlike older satellites that could only record narrow tracks, Cryosat-2 can turn those tracks into wide swaths, capturing full bands of surface height changes. After 10 years of collecting this data, researchers spotted 85 subglacial lakes that no one had mapped before. That brings the total number of known active lakes to around 231. And the key word there is active. An active lake doesn't just sit there like a pond. It fills, drains, and sometimes passes water along to its neighbors. In the new study, scientists didn't just mark dots on a map, they tracked full filling and draining cycles. They even mapped how some lake boundaries grew and shrank with time. They discovered 25 clusters where lakes act in groups and 5 new networks that behave like connected plumbing systems. It's not a scattered field of puddles. It's a living network, pulsing under the ice. Even more surprisingly, some of that hidden plumbing runs dangerously close to the coast. Earlier maps suggested the nearest active lake sat about 6 miles inland from the point where the ice begins to float on seawater. The new work found 6 active lakes within roughly 5 miles of that boundary, and 2 of them just 2.5 miles from it. That means under-ice rivers reach closer to the open ocean than anyone realized, which matters enormously for how fast ice can slide and how quickly it can feed the sea.
The Antarctica ice sheet, which has the biggest potential for sea level rise, is close to its tipping point.
The technology that made this possible sounds complex, but the idea is simple. Altimetry, measuring height from above, is like watching the chest of the ice sheet rise and fall as it breathes. Cryosat-2 bounces radar signals off the surface and times how long they take to come back. One pass gives a single line. Do that thousands of times, and you can track entire regions. Combine a decade's worth of those lines and process them into wide strips, and you get a continent-sized record of the ice's tiny movements. The signals are small, sometimes less than 1/10 of an inch per month, and the surface is noisy with wind-carved ridges and snowdrifts. That's where AI comes in. Instead of a scientist scanning endless graphs by hand, AI algorithms learn what a true fill and drain pattern looks like. A slow, bowl-shaped rise followed by a smooth dip, and filter out random surface bumps. The result is a far cleaner, continent-wide map that shows where the ice surface moves because of liquid water below. Airborne radar gives a second layer of vision. It sends radio waves down through the ice and reads the reflections from the bedrock. A wet bed, especially a lake with a flat water surface, shines brighter and smoother than dry, rough terrain.
And this goes from Antarctic sea ice over the ocean circulation over the Antarctic ice sheet, so the one that is...
In 2024, a team trained a deep clustering algorithm to scan those radar echoes. Instead of manually labeling every pixel, the computer groups similar features: bright and flat in one cluster, dull and rough in another. The clusters that match the pattern of known lakes reveal new ones instantly. It's like switching from reading a phone book to typing a name into a search bar. In the Gamburtsev subglacial mountains, this method didn't just confirm old lakes. It found brand new ones that no one had spotted before. Each tool alone tells part of the story, but together they become powerful. Altimetry shows what's changing right now on the surface. Radar shows what lies beneath. Combine both with AI, and the guesswork vanishes. And those rivers don't stop where the land ends. They pour into hidden spaces beneath the ice shelves, vast, dark caverns the size of cities. To see those places, and to understand what's flowing inside them, we had to send something else into the dark. Inside Antarctica's hidden ice caverns. Beneath the frozen skin of West Antarctica lies a hidden world few could ever imagine. It is pitch black, roofed by more than 1,000 feet of solid ice, and vast enough to hold an entire city. This is the secret space under the Dotson ice shelf, a submerged cavern where the ocean breathes in and out, sliding beneath the ice and quietly eating it away from below. No human has ever stood there. In 2022, a bright orange submarine did it for us. That machine was called RAN.
This sleek, state-of-the-art submarine named RAN was sent to explore the depths of Antarctica.
An autonomous underwater vehicle, or AUV, built to explore places no diver, no ship, and no camera could survive. Once it disappeared beneath the shelf, all contact was gone. No GPS, no radio, no live video. RAN was completely on its own, following a pre-programmed path through the dark, with only its sensors and memory to guide it. Its eyes were made of sound, a powerful multi-beam sonar pointing upward toward the ice. Instead of shining light, it sent out pulses of sound that bounced off the ceiling and came back as echoes. Line by line, those echoes built a three-dimensional image of the roof above, a map drawn in darkness. For 27 days, RAN roamed the under-ice world, covering more than 1,000 kilometers, about 620 miles, inside the hidden cavity. It reached 17 kilometers, a little over 10 miles, from the open sea into the black interior of the shelf. Overhead, the roof of ice was about 350 meters thick, roughly 1,150 feet. When the maps were published in July 2024, what they revealed stunned even the researchers. The ceiling beneath Dotson was anything but flat. It looked alive, rippled, sculpted, and strange. There were smooth terraces surrounded by sharp steps, long grooves and troughs, and broad, scooped depressions shaped like teardrops. Many of these melt hollows stretched from 65 feet to nearly 1,000 feet long. They weren't random. They formed in lines, pointing in the exact direction the water had been moving when it carved them. RAN's sonar had captured about 140 square kilometers of sealing, around 54 square miles, divided across the western, central, and eastern parts of the shelf's underside. To understand what shaped those features, RAN also recorded the ocean itself, the temperature, salinity, and flow speed of the water just below the ice. The sensors sat about 65 to 260 feet beneath the roof, close enough to feel the current that sculpted the ice above. The culprit turned out to be a familiar visitor to Antarctica's coasts, modified circumpolar deep water, or MCDW. It's a layer of relatively warm, salty water that creeps in along the seafloor, then rises where the cavity shape allows it to touch the ice. By warm, scientists mean just a few degrees above freezing, but that's enough. Where MCDW brushes the ice, the melting accelerates. Where the flow slows or spreads out, the melting eases. One of the clearest findings came from comparing the two sides of Dotson. The western side, where the strongest currents press in, was carved into wide, deep melt structures. The eastern side, which is thicker and colder, was smoother. That matched what satellites had hinted at for years. Dotson's underside was thinning rapidly, but unevenly. Now, for the first time, scientists could point to precise spots where the ocean's warmth was doing the most damage, and they could measure the shapes that damage left behind. Operating beneath an ice shelf is a kind of blindfolded navigation. With no satellite link and no radio, RAN had to rely on dead reckoning, tracking every small motion, correcting it with tiny sensor cues, and hoping the math held up. To trust the final map, the vehicle had to crisscross the same areas multiple times, from different angles, checking whether the same terrace or ridge appeared in exactly the same spot. That's why the mission took almost a month and covered hundreds of miles.
The RAN AUV has vanished beneath Antarctica's Doomsday Glacier.
But to grasp what drives that carving, you have to look beyond the roof itself, out to the open ocean, where the ice meets the sea. The boundary, where drifting sea ice meets the open water, is called the marginal ice zone, and it's a restless belt full of swirling eddies. These eddies are slow-spinning whirlpools, some miles wide, that transport heat and salt. When enough of them gather near a shelf front, they act like a conveyor belt, pushing warm water toward the ice day after day. Until recently, we had no good way to track those eddies around Antarctica. Clouds, darkness, and rough weather made it nearly impossible. That changed with Europe's Sentinel-1 satellites, radar eyes that can see texture on the ocean surface even through cloud and night. In 2025, researchers launched an automated detection system that uses modern object detection AI, the same kind of neural network that can spot cars or people in street photos, to find and classify eddies in those radar scenes. They trained it on more than 200 high-resolution images and sliced them into smaller sections so the model could spot even faint, tiny eddies missed by older methods. For Dotson, that breakthrough matters. If you can tell when warm eddies gather near the front of the ice shelf, you can predict when bursts of heat are being delivered to the gateway that leads into the cavern RAN explored. Every teardrop and terrace under Dotson's ceiling probably began as one of those heat pulses, an eddy outside feeding warmth to the currents inside. Put all the pieces together, and the hidden world starts to make sense. Outside, the eddies shove warm, salty water toward the coast. Inside, the shape of the cavity decides where that water flows, speeds up, and melts the roof. Where the current accelerates, the grooves deepen, and the teardrops sharpen. Where the flow spreads out and loses energy, the terraces flatten. After completing the 2022 mission and months of careful analysis, the team returned in January 2024 for one more dive, hoping to map the same regions again and see what had changed. RAN descended as planned. It never came back. The support ship waited at the pickup point, acoustic signals were sent, then drones and helicopters searched the area. Nothing. It was a hard blow, but the mission had already changed everything. Within a year, new funding was secured for a replacement vehicle, ensuring that under-ice exploration would continue. So far, we've heard machines under ice, mapped rivers under ice, and watched warm oceans carve the ice from below. But there's another kind of movement down there, one you can't see or hear. Ghost signals, moving beneath Antarctica. Beneath Antarctica's ice, there are things that move in ways no camera can capture.
Tiny plants and animals living embedded inside of glaciers, underneath the sea ice, and swimming in subglacial ponds.
They don't crawl or swim or ripple like water. They arrive as vibrations and flashes of light, faint signals hidden inside the ice itself. These signals tell us that something, some force, some pulse, some visitor, has just crossed the world below our feet. Down here, movement isn't just a body sliding forward or a current flowing beneath the shelf. It's the ground itself shifting in tiny slips, and it's particles from deep space slicing through a mile of solid ice, leaving thin streaks of light that only special instruments can see. Let's start with the slow earthquakes beneath the Willans ice plain. Picture an ice sheet the size of a small country, sitting on a bed of slick mud and rock. Most of the time, it creeps along so slowly you'd never notice, inch by inch, day by day. Then, twice a day, it jolts forward. These bursts happen when the friction between the ice and the bed suddenly gives way. The whole sheet slides about 1.5 feet in roughly 30 minutes. That may sound small, but it's a massive slab of frozen earth shifting all at once. These jolts, called stick slips, are triggered by the pull of the tides. High tide loosens the hold. Low tide finishes the job. Each time, seismometers and GPS units planted on the surface record the motion with eerie precision. But these slips don't happen cleanly or all at once. Before every big shove, smaller tremors crawl ahead of it, tiny ice quakes that march along the base in a slow, steady wave. Scientists call these migratory precursors. Think of them like sparks racing down a fuse before the blast. They tell us the base isn't simply snapping from stuck to sliding, it's loosening in a pattern, patch by patch, building toward that main release. To spot that organization, researchers needed help from machines that never sleep. In 2024, a new two-part, AI-based system changed how seismologists look at these signals. The first part is a detector that scans months of raw seismic data and flags every pulse that looks like an event, whether it's a sharp pop or a long rumble. The second part is a clustering algorithm that takes those flagged events and sorts them into families based on their shapes. It doesn't need a label for each one. It just groups them. This cluster looks like ice quakes. That one looks like wind noise. Another looks like long tremor bursts. What used to take teams of humans weeks of listening can now happen in hours. You can think of it like this. The detector is a bouncer standing at the door, separating events from background noise, while the sorter acts like a librarian filing each event into its proper shelf. Together, they create a timeline, a clear story of when the first tremors started, how long they lasted, and how they moved across the sensors. The Willans system has been doing this twice every day for years, and no two slips are ever identical. The beauty of this system is its reach. Seismometers don't need sunlight or calm skies. They can sit buried in snow through storms and darkness, recording every shake for months. Then, the AI combs through the data, pulling out thousands of events and arranging them into patterns. Once scientists know what a stick-slip fingerprint looks like, they can hunt for the same signature across other glaciers without needing as many instruments. It's not just research, it's reconnaissance, a way to predict when and how the base of Antarctica might shift next. Now, zoom out from the ice quakes and look at a completely different kind of invisible traveler. Particles from deep space, that plunge through the Earth itself and flash inside the ice. At the South Pole, more than 4,700 feet below the surface, sits one of the most extraordinary instruments ever built, the IceCube Neutrino Observatory.
The IceCube Laboratory, which is part of the larger IceCube Neutrino Detector, which is the biggest, most expensive experiment here at the South Pole.
Imagine a cube of perfectly clear Antarctic ice, nearly a mile on each side, threaded with 86 vertical strings. Each string holds dozens of glass spheres, called digital optical modules, 5,160 in all, each one a watchful eye. Together, they form a three-dimensional grid that watches for light no human can see. When a high-energy particle called a neutrino slams into an atom inside that ice, it triggers a faint blue glow known as Cherenkov light. The sensors pick up that light, and from its direction and brightness, scientists can reconstruct the path of the particle. IceCube doesn't just see from above. It sees through the planet. Some of the neutrinos it detects have crossed the entire Earth before lighting up the grid. Most of these ghostly messengers come from the violent hearts of the universe, supernova explosions, colliding black holes, or distant galaxies feeding on gas. Each flash inside the ice is a postcard from billions of miles away. Because neutrinos rarely interact with anything, IceCube has to watch constantly, catching the rare moments when one does collide. But to make sense of that flood of light pulses, human eyes aren't enough. The detector records millions of signals, most of them background noise. Turning those into direction and energy takes complex math. And in recent years, machine learning has become IceCube's sharpest tool. Deep learning models trained on thousands of examples now reconstruct tracks faster and more accurately than before. In 2024, a global challenge brought together the best AI solutions for this task, comparing how well they could determine each particle's direction and energy. By 2025, new hybrid models combined physics-based equations with AI intuition, cutting the analysis time dramatically. The same way AI sorts icequakes beneath Willans, it now sorts light flashes inside IceCube, pulling order from chaos. Thanks for watching. Now check out the videos popping up on screen for more unbelievable stories.